Welcome everybody, it's Ramchandra from CIVIL-MECH-MATHS Concepts channel. I have released 3 lectures on structural analysis, the most important topic for any engineer, for any engineering branch. And in this lecture, I have started with combined bending and torsion of beams. It's an advanced topic to analyze the effect of bending, shear and torsion and the effect of all these when combined, how to analyze the beam and how to design the beam. That's what is discussed here. Please view my channel, comment and review for improvement, and also please subscribe to my channel. I have released from my channel CIVIL-MECH-MATHS Concepts 48 lectures till now. Thank you. Welcome everybody, it's Ramchandra from CIVIL-MECH-MATHS Concepts channel, and today I will be discussing about the combined bending and torsion in beams. In the last 3 classes on structural analysis, I have given the introduction about the forces, their components in x and y directions, and a perfect frame in which number of members required is equal to 2j minus 3, where j is the number of joints. We have considered 7 joints truss. 2 into 7 is equal to 14 minus 3 11. 11 members are there in the truss. Hence it is a perfect frame. A perfect frame is a frame where number of members is equal to twice the number of joints minus 3. In that simple case, we have solved for the reactions by using the equilibrium equations. Sigma fx is equal to 0, sigma fy is equal to 0, and also sigma m is equal to 0. And we have resolved for the member forces, reaction forces, 11 members forces and 2 reactions, 3 reactions, total 14 forces we have resolved. And we took about 3 classes because each and everything like compression, tension, everything I wanted to explain in detail. In this also, we may take 3-4 classes for explaining the combined bending and torsion in beams. It is one of the most important topics. Studying bending separately, studying torsion separately, and combining them afterwards will not give the insight fully. Rather, I am taking an example where bending and torsion both are embedded in the system and we are trying to resolve it. For example, you may be surprised to know there are many structures, many engineering applications where bending and torsion both are applied together. We have simplified the engineering applications so that we can apply bending and torsion with a view or with a simplification that one does not affect the other. But however, the total combined effect will be there on the beam. For example, a cantilever beam is fixed at one end and free at another end. Let that beam be a circular beam. A beam can be circular, a beam can be rectangular, a beam can be hexagonal also. Nothing that a beam cannot have a different shape. A cross-sectional shape can be anything. A beam is there which is having a cross-sectional shape as circular beam and with a length L, let us say LB, length of the beam. And at the end of the beam, there was a lever fixed. There was a lever fixed. Fixed in the sense it is not fixed, it is temporarily put so that a torque can be applied. A torque can be applied and lever is BC, that is that length BC in the diagram is equal to, let me say, length of the torsion arm, or arm applying the torsion or applying the torque. Now, what is it? And a force P is applied at the end of the lever arm. Please try to understand the concept and geometry. AB is the circular cantilever beam. B2C is a lever arm on which at the end of the lever arm a load P is applied vertically. That load is even vertical to the cross-sectional area of the cantilever also. And the lever arm is exactly perpendicular to the cantilever. Section, exactly perpendicular to the cantilever axial portion. This degree is 90 degrees. And a load P is applied. Then what will be the effect of that load on the cantilever beam due to the application of load just vertical to the cantilever, but is applied at a distance of BC from cantilever on a lever which is connected to the free end of the cantilever. Here, the lever is going to create a torque at the center of the beam. At the cross-sectional area, free end center, cross-sectional area, free end center, that is point B, this lever BC is going to affect a torque. That torque is shown as T here. This is the torque which is effective because of the lever arm BC temporarily fixed to the cross-sectional center of the circular beam, cantilever beam, fixed at the other end A. This is the torque T. Now, is there any bending is applied here? Just to see. The geometry is like this. This is the lever arm. P is applied. This is BC. This is LB. Because of the lever arm, this lever arm is torsional length LT, bending length LB. Because of this LT, torsional length, arm length, lever arm is causing a torque of T is equal to P into LT. And this P, because it is acting exactly perpendicular to the horizontal axis of the cantilever beam, but at a distance of BC, but it is still connected to the cantilever arm, cantilever beam. That means the action of P is taken as good as it is applied on the free end of the cantilever beam. The final simplification of this arrangement will be cantilever beam with fixed end on the left hand side A and at free end B, a load is applied and a torque is applied. Because of this load, there will be a bending moment. Because of the lever arm, there is already a torque. That means torsion is there. That means it is a good example of bending and torsion. If you see, for example, live example or life examples, you can see shafts rotating in a machines, a wrench being used for twisting the beams, and a cantilever for aesthetic purposes is made on a pond so that people can go as if they go for some 1-2 meters inside the pond on the cantilever, and they can have a lever arm also, and they come back so that there will be a load is acting on the cantilever, and that load can be a perpendicular lever arm is also provided, then it will be a bending moment also, and there will be vibration of the cantilever also. That means vibration, bending moment, loading, torque, all these things are, this is explained in this example. Rather, this is an example of multiple forces acting on a cantilever beam, circular beam. And this is very common in mechanical engineering applications and also is common in civil engineering applications. This is one of the things very, very important for civil engineers and mechanical engineers. From here, this is an example which I have given you. From this example, quoting this example, we'll be moving forward to define bending, to define torsion, to define pure bending, to define pure shear, and to define the principal stresses, and to define the normal stresses, bending stresses, and shearing stresses in a beam. If I tell each and every item separately, what happens, you will not appreciate. The things will not be appreciated. Whereas a combined problem is taken and the problem is appreciated properly by everybody, then there will be a visualization that in connection with this problem, we will be solving the different types of structural analysis problems in strength of materials or structural analysis. Now, here we are required to go for some kind of sign convention for defining bending moments, shear forces. Because when a beam is subjected to an external load, there will be resistances to the bending by the internal stresses of the beam, and also there will be a resistance for shearing also till the beam failures. As a structural engineer, our aim is to see that a beam or a section doesn't fail under stresses, and every material, every cross section has its own resistance to the external forces applied. Whenever we apply certain external forces on the beam, there will be an internal resistance to it. That internal resistance will be to some extent after the external stresses increase beyond certain limit, there will be a failure to the beam section. That failure has to be avoided. For that, there are many theories have come into force, and there are many codes across the world. They are in place with suitable factor of safety, and those things, codes and factor of safety design, that we will be taking in the other part, second part of this structural analysis. The first part will be to analyze the bending stresses, to analyze the shear stresses, and to calculate the bending moment, and to analyze the combined effect of shear stress and bending stresses, and to analyze the combined effect of bending and torsion in a beam. Torsion is nothing but twisting. If a beam is twisted, what happens? Some fibers of the beam, if beam is twisted, what happens? Some fibers of the beam, they try to get relocated. Under elastic theory, as long as Young's modulus E is equal to stress by strain, and stress and strain are linear, then there can be restoration. Otherwise, there can be plasticity and failure. That fibers, they try to restrict, or they have certain capacity to restrict the tension and compression, the cross-sectional area of the beam. Now, we will go for the sign convention first. Then we will try to see, from simple cases we will try to develop the bending theory. Then we will go for shear force calculations. Then we will go for twisting of the beam, torsion, and we will combine all of them and see what happens. First sign convention is, if any beam section is subjected to loads in such a way that the movements, they try to create sagging at the bottom and compression at the top, that bending moment is taken as positive. And the bending moment has taken place in such a way, they act in such a way, the pair of the bending moment for a section, both sides bending moment will be there, or in such a way that tension will be at the top and compression will be at the bottom and hogging takes place, then that type of bending moment action is negative. And a shear force on left hand side acting upwards is positive, acting downwards in right hand side is positive, whereas left hand side downwards is negative. This you please take a note of it. It's very, very, very important sign convention. It is universally accepted sign convention, and this is very much required for all our calculations in structural analysis. You cannot neglect it. Again I will tell you, a bending moment happens to cause compression in the fibers at the top and tension in the fibers in the bottom. which is causing sagging in the bottom is taken as positive. A bending moment which causes tension in the top fibers and compression in the bottom fibers and causes hogging, it is taken as negative. A shear force acting upwards in the left hand side, downwards in the right hand side is positive. A shear force downwards in the left hand side and upwards in the right hand side is always negative. With this sign convention, we will move further. Here you just see, I want to explain sign convention is there, SFD and BMD we can draw. I want to explain something called supports. For example, a beam is there and a load is applied. This beam itself cannot stand in air, it will fall down. That means it requires some support. It requires some support so that it will stand like this in the shape. Let us say there is a support here like this. It is called as fixed support. I have given a fixed support. And here nothing is there, no support. It is called as free. No support. At free end in a beam, any point, moment will be 0. That we have seen in the plane trusses also. Moment at a joint, pin joint is 0. Like that at free also, at free end moment is 0. And Rx is equal to 0. Ry is equal to 0. At free end, all the values are 0. At fixed end, there is a moment. This is A. Because the structure has to be under equilibrium. Here everything is 0. Here everything is present. Ray, sorry, and it is Rax. That means at fixed end, it is able to hold the beam for the reason it is not allowing freedom for the beam to move or rotate. To move horizontally, to move vertically, or to rotate. That means there is a movement to stop the rotation. There is a vertical reaction to stop the vertical movement. There is a horizontal reaction to stop the horizontal movement if horizontal force is applied. Any kind of force you apply on the beam, if beam is fixed, it has 3 unknowns. If it has one fixed end, means one fixed end gives 3 unknowns, 3 reactions, 3 resistances. Something is fixed means we can say implies fixed, implies 3 unknowns, 3 resistances. What are these 3 unknowns or 3 resistances? Resistance towards upward motion, that is reaction towards upwards, that is RAY, upward or downward, vertical. Reaction towards horizontal direction, that is RAX, this way or this way. Reaction towards rotation, that is M. These are the 3 reactions for a fixed are required. Otherwise, the beam will not be under equilibrium, and that particular that particular is not called as a fixed end. That particular end is not called as a fixed end. If a end is called as a fixed end, it is shown as like this, and it is a fixed called as fixed. Now, fixed support. Now, next one, hinge support. This is hinge support. Hinge. In hinge support, what happens? There is a vertical reaction, but there is no horizontal movement. Hence, reaction is not required. There is no horizontal movement, hence reaction is required. RAY, RAX. Whereas this particular beam is there, that is rotated in any direction, so that M is equal to 0. Horizontal reaction is required to constrain the horizontal movement of the movement at this point. Vertical reaction is required to constrain the vertical movement, but movement is not there. There is no rotation. There is no restriction for rotation. Hence, for movement, M is equal to 0. There is no restriction. Whenever there is no restriction, reaction is not required. Whenever there is a restriction, reaction is required. Please remember this. Whenever there is a restriction, reaction is required. Whenever there is no restriction, reaction is not required. Reaction can be a force, reaction can be a movement. Now, in this, 2 unknowns, 2 resistances, because we are resisting it for horizontal movement and vertical movement. Reaction in vertical direction, RAY, reaction in horizontal direction, RAX, are required. And movement, reaction is not there, hence movement is 0. Now let's discuss another, because these are all required. These are all required for better understanding. Another support is roller support. In roller support, what happens? It is like this. That means it can move in this direction. We are not restricting it. And rotation also we are not restricting. M is equal to 0, we are not restricting. Rx is equal to 0 because we are not restricting. Only restriction we have is we are not allowing it to move in the vertical direction. Only one reaction required. Now can we summarize it? type of support, then symbol, and number and type of reactions required. For the definition. Now, what is the type of support? One is fixed. In fixed support, what is the symbol? This is the symbol. And number of type of reactions required? 3. What are that? RAX, RAY and MA. Let us say this is A. Second support is hinge. Hinged is shown as this way. There is no roller. Okay, it is hinge. Hinge, 2 number of reactions required. And what are they? RAX and RAY. MA is equal to 0. There is no moment at the, because it is allowed to move in the any direction for rotation. Translation is restricted. RAX, RAY, they are related to translational restrictions. Then roller, in translation also, already movement is not restricted. In this also, horizontal is not restricted, that means only one is restricted, that is RAY. RAX is equal to 0, M is equal to 0. This table you please remember this table and please understand this table. Now, the types of supports is over and the sign convention is over. Now, we will go to the understanding of the sagging and hogging moment. I feel you have understood well. In sagging moment, the bottom portion is under tension and I want to brief about the neutral axis. Beam is like this. Let us say, and it has a cross section. Let cross section be this. This is, let me say, A and B. Breadth and depth and breadth. This is the cross section. Here you will have a cross section like this. This is the cross section. I have little bit expanded this and we have written like this. And whenever there is a force, whenever there is a load, or whenever there is a bending moment, whenever the beam bends, either in a sagging or a hogging, what happens? There is one axis called neutral axis, where there will not be any change in the length of the fiber. Here what is happening? In sagging, lower fiber length increases, correct? Here in hogging, lower fiber length decreases, but upper fiber length is increased. Here upper fiber length, cross section area I am talking about, length decreases. Here upper fiber length increases. This I am only talking about the cross section. Now when something is decreasing somewhere and something is increasing somewhere, means there should be some place where this variation is not there. That means something is going from -3, decreasing means -3, let us say some value, and increasing means +3. Something is going from -3 to +3 means there is some point where it is 0. That means length remains the same. Please follow this. This is very important. Here, whenever length increases, what is that? It is a strain. It's a tensile strain. That means it is a positive strain. Here it is a negative strain, compression. Tension means positive strain. It is a negative strain. Whenever there is, that means strain changes the sign from positive to negative or negative to positive. But while changing, there will be a point where it crosses 0. It is like this. Let us draw a graph. Let us draw a graph. Load versus strain. That graph will be like this. That means from negative to positive, and it is passing through origin. But is it possible for every practical, in practice, this passes through origin? This is called as the neutral axis. Sometimes neutral axis doesn't pass through origin. Those cases for advanced studies. We will discuss here normal conditions where it passes through origin. Now, this neutral axis, strain is equal to 0. That means when strain is 0 means what is strain? Strain is change in length by, strain is equal to change in length by original length. If change in length is 0, 0 by L is equal to 0. That means strain is 0. Strain changing from positive to negative. Strain changing from positive to negative, from lower level to upper fiber. Then that is called as sagging movement, and that particular movement is positive, bending movement. When strain is 0, that axis is called as neutral axis. Wherever strain is 0, that axis is called as the neutral axis. The length of the neutral axis doesn't change throughout the length of the beam. Length of the neutral axis doesn't change, the position of the neutral axis doesn't change throughout the length of the beam. That means the fibers remain neither under the influence of strain nor under the influence, neither under the influence of compression nor under the influence of tension. Then that axis where strain is 0 is called as neutral axis. This is the meaning. You please try to correlate everything. Now we will go to next. You just see what I have told you. These figures I have drawn beforehand because so that I need not waste my time in the drawing this. A cantilever beam is there fixed at one end. There are 3 components which are to be found out. There are in a fixed end. There are 3 reactions. What are the reactions? In as far as forces are concerned, 3 restrictions rather. What are the 3 restrictions we have to solve? One is movement at the fixed end. horizontal reaction at the fixed end and vertical reaction at the fixed end. At free end, there are no restrictions. As movement is 0, horizontal force is 0, vertical force is 0. Under these conditions of external force. Now, sign convention. We will come to that part next, SFD and BMD. We will continue on this. What happens? For example, this cantilever beam is there. It is bent. It is bent like this. And we will take at a distance of x some small portion dx. And it is bent. As far as neutral axis is concerned, we have seen that neutral axis is constant. Neutral axis is the axis where strain is 0. And this is bent. In the top portion, strain is positive. In the bottom portion, strain is negative. Okay. There is one neutral axis passing through in such a manner that strain is 0. But the position of the neutral axis and this, both, we see that they are coinciding. But in reality, just see, for this small portion of dx length on the beam, there is a small, very small change, very small change, like this. For example, I will show you. Because of the external force, what happens? External load. This is the original beam with cross section. Now, this beam is slightly, I am showing in a microscopic manner. Don't think that it will be like this. I am showing it in a. That means an element of PQ or change it to P dash and Q dash. This will not be that much. I am just showing you. That means this is the distorted portion because of the force. This is the original portion. This is the distorted portion. That distorted portion is making an angle theta. Then, because the angle is very small, for small angles what it is? For small angles in radians, tan theta is approximately equal to theta in radians. Not in degrees, it is in radians. Tan theta is approximately equal to theta. This is. Then, whatever this curvature is there, here, some curvature of the whatever we say, there is a curvature, radius of curvature. It is having a slope of, it is having an angle of d theta. From the secondary school studies or geometry, we know this dx whatever is there, for this dx distance, this dx whatever is there, that is equal to radius of curvature into d theta, or d theta is equal to dx. Hence, the d theta by dx is equal to 1 by r. Please remember this. I am showing a little derivation. But if sigma is the stress there, I am talking about bending. Now only bending I am talking about. Under bending, if sigma is the bending stress, that is the stress, and E is the Young's modulus, Then what is Young's modulus? Young's modulus is equal to stress by strain. Then what is the value of strain here? Sigma by E, because E is equal to sigma by strain, which implies strain is equal to sigma by E, Young's modulus. Neutral axis is before the bending also straight and after the bending also straight. That's what we have. Neutral axis length is not changing. That means on the neutral axis, the strain is equal to 0. On the neutral axis, strain is equal to 0. Okay. When strain is equal to 0 on the neutral axis, automatically the stress also is 0 from this equation. That means strain and stress, they change the sign at the neutral axis. At a distance y in the beam, this is the beam, at a distance y in the beam, strain is equal to y by r. This y divided by this is r, strain. That whatever little deformation takes place, that deformation divided by radius of curvature is the strain. But strain is equal to sigma by E. That means sigma by E is equal to y by r. This is one of the famous equations. Sigma by E is equal to y by r. People call it as F by y is equal to E by r also. Very famous beam theory equation. Now, force, whatever force is there, we have applied the force here. P. Force is equal to, and that particular area of cross section, force is equal to stress into area. Stress into cross sectional area is equal to force. Now, bending moment is equal to force into distance. Just see how we are going to derive everything. Force is sigma into area. Distance is y, because we have considered y. Here you see, I will show you, this is y. This is the portion at which we have considered. Here you see, this is the neutral axis. When we consider bending stresses only, because load is like this, that means moment is like this, moment is like this, moment is like this means what is? It is negative. Negative moment means if it is like this, what happens? If both the moments act like this, what is happening? Compression at the bottom. We just see here. Compression at the bottom and tension at the top. That means from neutral axis there will be tension, and below the neutral axis there will be compressive stresses. Compressive stresses will be there in the below the neutral axis, and tensile stresses there will be there in the above the neutral axis in case of this type of arrangement. And at neutral axis, bending stresses are 0, strain is 0. Wherever bending stresses are 0, then shear stress will be maximum. What is the total stress? Total stress at any point is equal to bending stress plus shear stress under ideal conditions. When bending stress is 0, shear stress is equal to maximum. You see, shear stress will be maximum when bending stress is 0 or when the bending strain is 0. And on the neutral axis, shear stress will be the maximum. Please try to understand this. And When Bm is constant, it is called as a pure bending, and Bm changes, that is called a non-uniform bending. This I will explain you. For example, a simply supported beam, there are two loads P and P at same distances, then BMD will be this portion where shear stress is 0. This portion is called as pure bending. Please remember this concept also. Here it will be non-uniform bending, here it will be non-uniform bending. There may be questions in your examination or in an interview, that is, explain the pure bending, and also when shear force is 0, what happens to bending moment? Bending moment will be constant, and that particular portion is called as the pure bending. And when on the neutral axis, what happens means, on the neutral axis shear bending strains will be 0, bending stresses will be 0, shear stress will be the maximum. And from a distance of y from the neutral axis, what happens? Y from a neutral axis, F by y is equal to E by R, or sigma by y is equal to E by R. And when next we will go for this, sigma into area is equal to force, stress into area is equal to force, because stress is equal to force by area, into distance is y. That y distance we have taken here from this diagram. From this diagram, y we have taken y. That means at a distance of y from the neutral axis, at a distance of y from the neutral axis, it is from the neutral axis, bending moment is equal to force into distance. Force is nothing but, we have just now found out, force is equal to sigma into A. Sigma is nothing but E by R into Y. This is equal to sigma by Y. E by R into Y is equal to sigma is equal to E by R into Y. You just see this. Sigma is equal to E by R into Y into area into Y. That is distance. Area into y square. What is area into y square? This is the second moment of inertia of a cross section. That we will denote it as I, second moment of inertia. Second moment of area we can even call it as. It has in SI units m to the power of 4. M to the power of 4 as units for I, second moment of area. Second moment of area. Some people call it as moment of inertia also. That means m is equal to E by R into I, where R is the radius of curvature. Hence, what is E by R? E by R is nothing but F by Y or sigma by Y. That means this is the most important formula you should remember. M by I is equal to E by R is equal to sigma by Y. M by I is equal to E by R is equal to sigma by Y. Or M by I is equal to E by R is equal to F by Y. This is the most famous equation for solving the bending stresses in beams. M by I is equal to F by Y is equal to E by R. M by I is equal to F by Y is equal to E by R. M by I is equal to sigma by Y is equal to E by R. Now, sigma is equal to M by I into Y. For some time, E by R, let's forget. Sigma is equal to M by I into Y. What is Y? Y distance. Y distance will be maximum when, you just see, it will be maximum when Y is equal to D by 2. If it is a circular or rectangular or normal, y is equal to d by 2, y max. Do you agree? Even for circular it is diameter, for rectangular it is depth by 2. Because neutral axis is passing the centroid. Now you just see. y is equal to d by 2. If you take that, y maximum will be sigma maximum, m maximum will be maximum allowed. That maximum bending moment allowed is equal to maximum bending moment allowed is equal to sigma into I by y. Sigma into I by y. This is very, very important equation. Maximum bending moment allowed. From the external loads, you can calculate the bending moment. And from the cross-sectional area, you can calculate the I and y. And from the codes, you know the maximum allowable stress, bending stress. Then maximum allowed bending moment is equal to sigma maximum bending stress into Z. That implies M maximum allowed is equal to, please see this, understand this, sigma maximum from the codes allowed into Z. What is Z? Z is a constant for the given cross-sectional area. Z is equal to I by y max. Under normal conditions, y max is equal to Z is equal to y by I max. I think this paper is full now. That means Z is equal to y by I by y max. Now, from the standard books, you can get the value of I for various cross sections. That you do yourself. And Z is equal to I by y max, and this m max allowed is equal to sigma max allowed into Z. Now, for a circular cross section, y max is equal to d by 2. What is the value of I? I is equal to pi by 64 into d to the power of 4. Hence, sigma, that is stress allowed, bending stress allowed, is equal to 32 m by pi d cube. Either way, you can find out the bending stress at a particular section because of some bending load applied. You can calculate the bending moment. From that, you can get the bending stress, and you can compare it with the code allowable stress. Then, if you see whether your bending stress is within the limit or not. If it is crossing the limit, means that particular section design is wrong. If bending stress code provides allowable stresses. If sigma bending allowable is greater than sigma calculated, it is okay, design is okay. If sigma, I am talking only about bending, I have not taken even shear now. Allowable is less than sigma calculated, this is not okay. Please try to understand this. Now, what is sigma calculated? What is that? M by Z. Bending moment by Z. What is Z? Second moment of inertia divided by y. Max. And for y max is equal to d by 2 for rectangular cross section, and y max is equal to d by 2 for circular cross section. And for other cross sections, you please try to find out from the regular books. Please try to find out from the regular books. The Z is called as section modulus. For various geometries, section modulus values are given in all the standard books. And Z is equal to, for circular, pi d cube by 32. Here you see, we have done it. Pi d cube by 32. Sigma is equal to m by z. For rectangular, you can find out from for other sections also you can find out. So that semicircular sections, rectangular sections, hollow sections, you can find out the section modulus. Once you have the value of the section modulus, you can find out the stress. You can calculate the stress with the help of the bending moment, calculating the bending moment from the load applied. For a rectangular section, I is equal to BD cube by rectangular, I is equal to BD cube by 12, which I have explained previously in all my classes, and y is equal to d by 2. That means Z for rectangular is equal to BD square by 6. These two famous values, please remember. And others also you can find out from your own, so that you can find out the, like what you call hollow means d do square do cube minus di cube. Then you can go for this rectangular, then you can go for semicircular. As a homework, find Z for hollow, circular, 1, 2, semicircular, solid semicircular. You can have any shape. You can define. And Z values are available in standard books. Find out from them and calculate the stress, calculate the bending moment. Bending moment divided by section modulus gives you the bending stress. Just check up what is the value of the bending stress. And bending stress and shear stress, that is the total allowable stress at a particular point. If they are more than the allowable stresses in the beam as per the code, then reject the design. If it is less, means accept the design. This is about the bending stresses. I have given the outline of the bending stresses. Next, in the next class, I will be going for the shear stresses. Then once shear stresses are over, then we will go for this combined, then torsional. What is about the twisting and torsion? Then we will go for combined bending and torsion in beams. One by one we will go. I feel it may take 4 to 5 lectures. Please bear with me. I want to go in detail and explain you in detail. And in between also 1 or 2 important either engineering services UPSC or GATE or some SSC JE conventional paper, some good structural analysis, numericals we will try to do. In the next class I feel we will go for one numerical either from UPSC engineering services or GATE or from SSC JE advanced paper 2. But as far as the paper 1 is concerned in SSC JE, whatever concepts I am discussing here, please note them and ensure that they go into your understanding. SSC JE, UPSC, Civil Services or ESE and GATE. I found out very good numerical. In that also we will try to learn the concepts so that we can recoup these concepts, recollect these concepts and we apply them so that you will be thorough. Best of luck to everybody. It's Ramchandra from CIVIL-MECH-MATHS Concepts channel. If you feel the way I explain the concepts to you is good, please view, review and comment on my previous videos also. Please see that these concepts will be going into your friends and other persons of need so that everybody will be taking help from these concepts and clear their concepts and do better in the examination. Let's help each other and subscribe to my channel to get the regular updates. Please view, review, comment on all my videos and subscribe to my channel CIVIL-MECH-MATHS Concepts for regular updates, and please comment so that I will improve on my way of teaching or way of lecturing or way of describing the ideas of the concepts in engineering. And this particular lecture is not only useful for civil engineering, it will be useful for mechanical engineering also. And this what you call shafts, circular shafts with lever arms and also bending, combined bending and torsion in beams is one of the major topics and very prominent applications in mechanical engineering, also in civil engineering, but mechanical engineering has got many applications. And I want to close today's class with this note. Please try to understand the fixed hinged and roller support differences. Please try to understand the section modulus, how to calculate it, and please try to understand what is the neutral axis and how neutral axis is to be found out. Please try to understand how is m by I is equal to f by y is equal to e by r, or m by I is equal to sigma by y is equal to e by r, how that particular equation has come, what is its importance, and some bending moment and shear force diagrams I will take up in the next class after the numerical. We will do in the next class a good numerical on this. Okay, best of luck to everybody. Please subscribe to my channel. It's Ramchandra again from CIVIL-MECH-MATHS Concepts. Thank you for listening to me. Thank you.